Hello everyone. So by now in this course you have learned or you have heard about the term pyrolysis multiple times, right? Pyrolysis we talked about when we were talking about getting graphite from needle coke, or when we were talking about the pyrolysis of hydrocarbon gases for obtaining pyrolytic graphite, which can then be converted into highly oriented pyrolytic graphite. We will also be talking about this particular process multiple times because you see, whenever we are making synthetic carbons, what we have is an organic material as a precursor. Now this organic material can be a solid polymer, it can also be some liquid petroleum material, or it can also be a gaseous hydrocarbon. In all cases, we are getting different types of carbons, but our precursor is a hydrocarbon, and the process of conversion or getting the carbon from this precursor is your pyrolysis, the fundamental process. You have the heat treatment, but the most important part of the heat treatment is when you're getting rid of your non-carbon atoms, and then you have the formation of carbon-carbon bonds. So this is why pyrolysis is very important to us. In this particular lecture, what I want to do is I want to tell you what is pyrolysis. So you know already what is the region, in the heat treatment, which region, let's say from room temperature until 700, 800 degrees, that is the region where you have the breakage of the bonds. You have larger hydrocarbons converting into smaller hydrocarbons. But you also know that this is just, this is not the only thing that's happening in your heat treatment. If you keep on further increasing the temperature, you have carbon-carbon bond formation. At some point, if you want to convert your material into graphite, you may have to go to very high temperature. So this is your entire heat treatment process. Pyrolysis in particular is the part where you have the thermochemical decomposition of your organic material. This needs to essentially take place in the absence of oxygen. So this is the definition. Now as I already mentioned, that your organic material can be gas phase, liquid, or solid. Okay. In the absence of oxygen, this is also very important. If you have any oxygen present, then the chemical reaction that will take place will be combustion and not pyrolysis. Now you will find some examples. For example, when people do waste treatment, what they do is they're actually now converting a mixture of a lot of materials, mostly organic materials, but the waste materials, urban solid waste, that contains a lot of things, and we don't know the exact composition of these materials. At that time, these things are heated. This mixture of materials is heated up to not very high temperatures, but 600-700 degrees, and then that process is known as pyrolysis. However, often you may have some oxygen also present in that process. There, actually, what is happening is, at the end of the day, you have a combination of pyrolysis and combustion. Since your material mixture is very complex, you cannot really separate the pyrolytic and combustive decomposition of the material, because this is a complex mixture. So you end up calling it pyrolysis, but actually this is pyrolysis plus combustion. Also, in the case of waste management, our primary goal is not to make carbon, but rather to whatever were the byproducts of our current process, the tars and gaseous hydrocarbons. These were the byproducts when we are making carbon. Now those byproducts actually become the primary product, and the char or the carbon becomes sort of the byproduct. In the case of waste treatment, that is not something that we are going to discuss in detail in this particular course, because this is a carbon manufacturing course, right? So pyrolysis in the context of carbon manufacturing, that would be just, we will take generally very well known hydrocarbons, and also we will optimize the parameters in such a way that the carbon we want to obtain also has a given geometry, given morphology, given microstructure. Okay. Some examples of solid, liquid, and gas phase pyrolysis. Solid phase pyrolysis, already, we've already talked about needle coke and the conversion of needle coke into graphite. Also, when we were filling the pores of the needle coke, if you remember, we filled them with either pitch or some sort of resin. These resins can also be hardened by curing. And in that case, the pyrolysis or carbonization of these resins is also, an example of solid phase pyrolysis. In fact, we are going to learn about this technique also again when we talk about microfabrication using carbon materials, because also in that case what we are doing is we are taking a phenol formaldehyde resin, cross-linking it to convert it into a solid form, and then we are carbonizing it. So these are examples of solid phase pyrolysis. Okay, how about liquids? So you already know that petroleum pitches can be carbonized. They contain up to 95% carbon, and we often use them for, we mix them with our needle coke, or we sometimes also use them for pore filling. You will also learn that we make carbon fibers from them. So these are the examples of liquid phase pyrolysis. Some polymers can also be liquid when they are being carbonized. Gas phase pyrolysis, well, you know already. We can use methane, we can use acetylene, we can use benzene, we can even use vapors of certain light alcohols, for example, and then we can, at higher temperatures, we can crack these hydrocarbon gases, and then we can get carbon out of it. This process is also known as chemical vapor deposition. So chemical vapor deposition is basically a more general term. So you can also, for example, make silicon, or you can chemically deposit a metal oxide semiconductor. That will depend on the precursor that you have. But when we say pyrolysis, then we are very specifically talking about pyrolysis of a hydrocarbon, and then we are talking about carbon deposition. So yeah, okay. Now the goal of this particular lecture is to tell you what happens during pyrolysis. So I had briefly told you that you have, this is the region where you have the cleavage of the bonds. And cleavage, well, typically will be carbon and non-carbon atoms, heteroatoms. There will be the bonds between them will break. Different bonds break at different temperatures. There are no very well-defined temperatures, but you do know a temperature range where a certain type of bond will break. Okay. However, now for gas, solid, and liquid phase materials, this mechanism will also differ slightly. If you have larger hydrocarbons, then what will happen is they will break into smaller hydrocarbons. The smaller ones will further break into, even smaller. So this fragmentation process will go on in the case of heavier hydrocarbon molecules. However, if you already start with a methane or very light hydrocarbon molecule, in that case you're not going to get lighter hydrocarbon molecules, but you may actually, the carbon heteroatom bond will break also in that case. And you may sometimes also have non-carbon atoms just being released in the form of some gases. Okay, this will also happen in the case of polymer pyrolysis. But so what will happen is when you have this fragmentation process, at some point, whatever is a very volatile hydrocarbon or light, so volatile hydrocarbons are typically then the much lighter ones, they will leave your material. Okay, these things are happening. What else? So we talk, this is more like the cleavage process. But is there also some cyclization happening at the time of pyrolysis? Now, what is cyclization? We know that what we get out of pyrolysis, or at our end product, is carbon. Okay. Now this carbon often has hexagonal structures, graphitic carbon. As you keep on increasing the pyrolysis temperature, you get more and more graphitic content. But to start with, also you need to have certain hexagons, and these hexagons are being formed at some point. What is that point? This depends on the precursor material. You may have a precursor with a lot of aromatic structures. In that case, you already start with some, hexagonal ring-like structures, cyclic structures. But you also have aliphatic polymers. For example, polyacrylonitrile. We are going to discuss that when we talk about carbon fiber fabrication. That is not an aromatic material. What happens if you start with a hydrocarbon like methane? So in these cases also, what's happening is at some point there are some cyclic structures being formed, and the cyclization process also often already starts at the pyrolysis time. So when some molecules are being fragmented, there are also some molecules that have converted into radicals, and these radicals attach with each other and they form larger cyclic structures which may still contain hydrogen. And the hydrogen may cleave at a slightly higher temperature, but the some fraction of cyclization already takes place in the at the time of pyrolysis. What often happens is it's not just one of these three processes, but all of them. They're all happening at the same time. In fact, this is what makes your pyrolysis a very complex process to understand. I'm saying complex because think about a heavy hydrocarbon material. You have this hydrocarbon, and then you get smaller hydrocarbon. Now those are also breaking into smaller pieces. We don't even know a lot of these materials. It's really difficult to characterize all of them because they are not just primary but also secondary. and tertiary reactions that are taking place. We don't know the rate of each reaction because there are multiple reactions. Some may be first order, some may be second order, and we don't even know exactly how many things. Also, these reactions are influencing each other. The byproduct of one reaction might actually influence the reaction conditions for another one. So this is sort of a very complex chemical process to understand, especially when we are talking about heavier hydrocarbons. In the case of smaller hydrocarbons like gaseous ones, it's relatively easy to understand. In fact, I have taken the example of methane in this particular case, which is also a precursor for getting graphene sheets. But this is something we are going to talk about in our graphene section. But the fundamental process remains the same. This is the pyrolysis of methane, which deposits certain type of carbon layers. These are graphitic carbon layers, but turbostratic, so randomly arranged on top of each other. Now, this is what we call graphene. But if we further do hot pressing or annealing of these carbon layers stacked on top of each other, then what we get is pyrolytic graphite, and further heat treatment will yield highly oriented pyrolytic graphite. So right now our goal is to get graphite, and that is why we are not talking about graphene, but the process remains the same, and the fundamental the principles remain the same. Okay, fine. So what is it, what property determines which molecule will be formed, which compound, let's say, will be formed? There is something known as the enthalpy of formation. We also talked about it when we were discussing how to convert why doesn't graphite convert into diamond naturally, or diamond convert into graphite naturally. So at that time also we learnt about this. Basically, again, just to remind you, this is the change in enthalpy for obtaining 1 mole of a certain compound from its elements, from its components. Okay, when they are like infinitely away from each other, you bring them together, make the compound 1 mole of this. The enthalpy, the change in overall enthalpy for doing this will be known as the enthalpy of formation. How does that relate to pyrolysis? Okay, so when you take a polymer hydrocarbon, heavy hydrocarbon, let's say, now at a certain temperature, let's say 500 degrees, what will happen to it? Some byproducts are going to be formed, some small hydrocarbons are going to be formed. Which hydrocarbons? Will you get benzene, or will you get methane, or will you get some other smaller polymer-like structure? Or what is it that you're going to get? That will depend on what is the enthalpy of formation of that particular product at that given temperature. So this is very important, that we are not talking about room temperature enthalpies anymore. We are talking about the enthalpy at 500, 600, whatever temperature. So if any particular compound has the negative enthalpy, then it is a spontaneous reaction. Then there is a probability that it will be formed. Okay, so if at 500 degrees methane has a more negative value of its enthalpy compared to, say, benzene, then there is a higher probability that methane will be formed as the byproduct. So this is one thing. Okay, however, what happens if I take methane itself as my starting material? In that case, if I'm talking about the pyrolysis of methane now, pyrolysis of the gaseous hydrocarbon, in that case, I will have to figure out the temperature where the enthalpy of methane formation becomes positive. That means this is not a thermodynamically favorable reaction anymore. There is a higher probability that now methane will decompose. So these are the two important things based on the energies, enthalpies required to form something. Then accordingly that compound is formed or decomposed. Okay, so this is basically what we are going to talk about in the next couple of slides. And you should remember that right now we are talking only about, so I will take the example of the pyrolysis of methane. In the case of polymer pyrolysis, the process slightly differs. So here in this diagram you see that I have plotted the enthalpies of formation of various hydrocarbons, light hydrocarbons, with respect to temperature. So there is a temperature line here. Okay, so with respect to temperature, you see how do the enthalpies change for every hydrocarbon. So here is methane, and this is our methane line. Okay, you see that methane line. So methane at lower temperatures, this is the enthalpy of formation of methane is negative. Okay, so we need to basically see that what is the temperature at which we are talking about, because during pyrolysis we are increasing the temperature of the process. Okay, for any given temperature, whatever is the most stable hydrocarbon at that particular temperature will have the highest probability of formation. Okay, let's say when we take the example of methane, you see that this is the methane line intersects with your temperature line at around 500 degrees centigrade. What does this mean? That below 500 methane is very stable. It does not decompose. In fact, it is more stable even compared to carbon and hydrogen, and that is why instead of carbon and hydrogen you will rather have methane. Okay, so up to 500 degrees, it's not exactly 500, it's actually 520, something like that, but approximately till 500 methane remains very stable. However, what happens above this temperature? Now methane becomes unstable compared to carbon and hydrogen. However, if you compare it with other hydrocarbons, it is still the most stable one. So now there is a possibility that methane will split into carbon and hydrogen. However, if you are doing solid pyrolysis, polymer pyrolysis, if you have to get a hydrocarbon, then this is still among the hydrocarbons, still it remains the most stable one. Okay, now you see one more interesting thing here, that above, now you go to 800 degrees, somewhere here. Okay, now after that, other aromatic hydrocarbons such as naphthalene or benzene, now they are less positive. Their enthalpies are less positive compared to that of methane. So now there is a higher probability that you will have benzene or naphthalene rather than methane present at that temperature. Now it is not the most stable hydrocarbon anymore. Aromatic hydrocarbons are actually, after 800 degrees, aromatic hydrocarbons tend to become more and more. So when we say aromatic, there is some cyclization that is possible. That is what I was saying. So above 800, cyclization is possible, or that is more favorable. Okay, so this is how you're going to decide at what temperature there is a possibility of obtaining solid carbon particles from any particular hydrocarbon. So this you can do also for other hydrocarbons. Now whatever is shown, ethane and ethylene and so on, you can also see that some hydrocarbons, even at room temperature, they have a positive enthalpy of formation, and some of them are negative. So as you keep on increasing the temperature, of course you will also play with other parameters. Now, so from here we understand that at what temperature it is possible to decompose methane. Okay, but is that it? Now what we need to do is we need to somehow collect our solid carbon from this methane. So what do we do next? Now there is something known as the solubility of carbon solubility in gas phase, and that is something that now becomes an important parameter. So we know that now there is a possibility that methane will split into carbon and hydrogen at a certain pressure and at a certain temperature. So the optimization of this temperature pressure condition is now important to us. Okay, so this is determined by the solubility of carbon in gas phase, or carbon solubility. Okay, this basically is defined as the total amount of gaseous hydrocarbon which is in equilibrium with the carbon, solid carbon. That is known as the carbon solubility in that gas phase. Okay, there are certain curves that you see in this diagram. Okay, you see that this is the fraction of your carbon, and this is your pyrolysis, or this is the heat treatment temperature. So now maybe this is not, you may or may not call it the pyrolysis region. In the pyrolysis region, we got some carbon hydrogen from our methane. Now this is the part when we are going to do the deposition. Okay, you see that there are these different curves at different pressure values, and these curves are basically known as the carbon solubility curves in the gas phase. And you see that all of them show a certain minimum value. They show a certain minima which is different at different pressures. So at approximately 10⁻⁻2 bar, The minima is at around, let's say, approximately 1100 or something like that. What does this mean? This means that this is the optimum temperature for collecting the solid carbon. This is the optimum temperature where you should perform the deposition operation. Okay, this is also one more interesting thing that you see from these curves is that as you keep on increasing the pressure, the minima value keeps shifting right, towards the right. So, for example, it goes all the way to 1900 degrees centigrade. What we want to do is when we are performing pyrolysis, we want to actually start collecting our carbon as soon as possible. So if we want to do it at lower temperatures, let's say 800 degrees or 700, we already want to start collecting the carbon. What is the option? What we can do is we can keep on reducing the pressure. So 10 power minus 2, already it is 1100. If we go to 10 power minus 3, minus 4, minus 5 and so on, we go in the millibar temperature pressures. In that case, you can slightly further shift your curve towards the left. So basically what you can get is now at 800 degrees, for example, you will be able to collect the carbon that is deposited from your methane. Okay, so this is basically the idea. This is basically the mechanism. And if you understand that, and then you can play with these parameters, then you can find the optimum conditions. In fact, that is how the modern day CVD is developed. In the past, we were only performing pyrolysis of gaseous hydrocarbons for making graphite, but then people realized that okay, by changing these pressure conditions, by changing all the parameters, we can actually get single layers of this graphene-like structure. Then can we also utilize those things? And in fact, nowadays we use graphene for a number of applications, but this is by optimizing these parameters which are shown here, then you can actually get better carbon, get more graphitic carbon, get single layers of carbon, get few layers of carbon, and so on. Okay, now there is one more small thing that I said that carbon nanomaterials and so on, the single layer of graphite that is known as graphene and so on. One more important thing is that these gases, when the solid is formed, when the solid carbon is formed, and then you also have some hydrogen in the process, right? So your methane splits, you have some solid carbon, you have some hydrogen, and you also have still some methane in your system. And if you are working with not just methane but slightly larger hydrocarbons, for example, alcohol vapors and so on, you may also have another hydrocarbon present in your system. All of these things will have their partial pressures. So it will never happen that at 1000 degrees centigrade inside your reaction chamber you have only solid carbon, or you have only methane, or you have only hydrogen. You will typically have a mixture, so you will have a partial pressure of each one of them. And that is why it becomes also very important that you the solubility of carbon there, it becomes very important. That you need to know at what point do you have the highest probability of getting highest partial pressure from your carbon vapors. Now these are not vapors, so this is also one more thing. Is it solid carbon or it is vapor phase carbon? So when we were talking about the phase diagram of carbon, we did discuss that is there a possibility of having vapor carbon in the CVD chamber? The answer is yes. In this particular case, you may have some vapor phase carbon when it is forming from methane. But vapor phase carbon is highly unstable and it immediately tries to convert into solid phase. And then, of course, when we have a substrate and we are collecting it on that substrate, then what we get is the solid phase carbon. But it's not impossible that in this mixture you have certain vapor phase carbon as well. Okay, so little more about this mechanism of carbons and of pyrolysis. So we already now talked about the pyrolysis of methane. In general, you can this is also kind of obvious to you that pyrolysis can be divided into two steps. One is the decomposition of hydrocarbon and two is the formation of carbon. Okay, formation of carbon continues to take place even after your pyrolysis is over, or that range of temperature is over, even at higher temperatures. But the carbon formation is one thing, and the rearrangement of carbon bonds is another. So when we are talking about carbon formation here, we are talking about the formation of carbon from the hydrocarbon, and then whatever happens, the carbon-carbon bond formation and rearrangement, reorganization, that happens at higher temperatures. In fact, we will also talk about that, the graphitization, carbonization and graphitization steps. Okay. Now, but in this particular case, as I mentioned, that there is also certain cyclic compounds that are being formed. This is the number 3. So on the first slide, we discussed that there are a couple of things that happen during pyrolysis. So we have already talked about the decomposition aspect. Now let's talk about this carbon formation aspect. You get certain carbon, but also there are, you here and there may also have these cyclic compounds being formed. Okay. Now, this will depend on the precursor and the nature of precursor very strongly. But I have just taken an example, a simple example of benzene, not very complicated hydrocarbon, because you can see how the benzene rings split, and then they form a radical, and then this radical can actually lead to a number of different cyclic structures, which will then lose their hydrogen at higher temperatures, and then they will yield carbon which has those many rings. Okay, so where is the picture? Yes. So here you see, you have in the beginning, you have this one benzene molecule which loses one hydrogen at higher temperatures. And the temperatures you will now understand from this enthalpy diagram, at which temperature will benzene decompose. Okay. Now you have a radical, and then you don't have one radical, but you have multiple such radicals which can attach to each other, which can organize themselves to give you so many different organic compounds. These are still hydrocarbons. These are still, they contain hydrogen. So this does not happen at very high temperatures, 300, 400 degrees, or this is even, these are very initial stages of benzene pyrolysis, but you already have cyclic compounds being formed. So there are actually many examples of, if you take naphthalene, if you can take any of these simpler aromatic hydrocarbons, and then you will immediately see that they lead to cyclization. However, aliphatic hydrocarbons also may lead to cyclization. We are going to learn about that in the carbon fiber. For polyacrylonitrile is a good example for that. Okay. Yeah, so basically pyrolysis liquid and solids, as I already mentioned, is a little more complex, and that we are going to learn about them in some other lectures. What is important is the further reading. So there are these 2 books that I have mentioned here, but I have tried to collect some information also from these books and presented it here, but these are for further reading.